Okay, let's see the geometric interpretation of decision trees. To keep the things simple, I'm only considering a binary tree. There are some variants of decision trees that allows us to make the multi-way splits. But here I'm only considering a binary tree. And also I'm only assuming two features, feature F1 and feature F2. And also I'm assuming the target variable to be of binary. That is, the target variable can contain either positives or negatives. So this is a simple a toy decision tree that I have considered here with two features on a binary classification problem. Now let's try to break this down geometrically. So let's try to parse this tree from the root node. So root node says if feature F1 is less than or equal to 5, then go to left hand side. If this condition is true, we go to the left hand side of this tree. If this condition is false, we go to the right hand side of the tree. So now let's see how to represent this geometrically. So here it says feature F1 is less than or equal to 5. If it is true, we go to left hand side. If it is false, we go to the right hand side. But if we go to the right hand side, there aren't any more conditions to check because we reached a pure node. In terms of decision tree, a pure node means all the samples in this node belongs to the same class. You cannot break these samples anymore down using their target because every sample belongs to the same class. In this case, every sample belongs to the positive class. So now let's draw a line parallel to y-axis. So it says if this condition fails, we go to the right hand side. That is, if feature F1 is greater than 5, then we go to the right hand side where we classify the point as positive. So now if you see the same thing geometrically, if the feature F1 is greater than 5, that means right hand side to this line. So all this space will become positive. So I'll just represent this with green color. So everything that we have here and this entire thing, so this whole thing will become positive. Okay. So any sample that satisfies this condition, that fails this condition and comes to the right hand side of the tree, comes to this specific space in the geometry. Okay. So here, if a point comes here, then it's been classified as positive. Let's say this condition is true. That is, the feature F1 is less than or equal to 5. In this case, we'll go to the left hand side of the tree, where we again check for a different condition using feature F2. So if feature F2 is less than or equal to 4, then again we go to the left hand side of the tree. I'll just repeat once again. If feature F1 is less than or equal to 5 and feature F2 is less than or equal to 4, then we come here. And when we come here, there aren't any more conditions to check because again we reach the pure node. In case if this condition is false, that is, if feature F1 is less than or equal to 5 and feature F2 is greater than 4, then we come to the right hand side of the tree where every sample belongs to one class, where here in this case, every sample belongs to the negative class. So let's just try to draw this geometrically again. So now I'll draw a line that is parallel to feature F1. So this is the line. So if feature F1 is less than or equal to 5, that is left hand side to this line, and feature 2 is less than or equal to 4, that is below this line, that is this specific square that we have here. So this is what I'm referring to, this positive class. So now similarly, if a point falls into this space, again it's been classified as a positive sample. Okay. And let's say if feature F1 is less than or equal to 5, we come to left hand side of this line. And if feature 2 is greater than 4, we go above this line, that is this specific space where every sample is negative. So I'll just represent this with negative, that is red color lines. So this is negative space. So this is how we geometrically interpret our decision trees. And if you observe this closely, so what are these decision boundaries? So these decision boundaries are just lines in this case. So this is a 2D plane. I mean, this is a two-dimensional geometrical space where every decision boundary is a line here. So from this, we can say that, so whatever decision boundary we have, so we can just say all these decision boundaries are axis parallel lines. Okay. So just to convert this decision tree into a geometric space, we just end up with a parallel axis parallel lines. So now, if you just extend this concept to 3 dimensions or more than 3 dimensions, then these lines will become planes, and planes will become hyperplanes. Okay. So in the higher dimensional space, instead of calling them as axis parallel lines, we usually call them as axis parallel hyperplanes. So hyperplanes in case of 3 dimensions, lines in the case of 2 dimensions, planes in the case of 3 dimensions. If you go beyond 3 dimensions, then it will be hypercubes or hypercuboids. Okay. So this is how we geometrically interpret our decision trees. And if you are interested in looking at the code, there is a simple function in scikit-learn which is called a decision boundary display. So there is this function in scikit-learn where you can plot the decision boundary of any algorithm, of any model. So here in this case, they're trying to build a decision tree classifier on a iris dataset, and they are plotting a pairwise plot. Like for every two features, for every pair of features, they have plotted this diagram here. And again, if you observe closely here, all the lines that you have here, that is all the decision surfaces in these diagrams are lines, because it's a 2D space, it's a two-dimensional space. So the decision surface in the decision tree in the case of 2 dimensions are simple axis parallel lines. So that's why you just observe the lines here. Whatever decision boundary you observe here, everything is a line. There aren't any curves here. It's all about lines. Thank you.